So very simply, guys, follow instructions. Right? So when you see something on the test, you answered it correctly if you followed instructions. If I say find the derivative and you found the derivative, that's absolutely fine. Right? I maybe you found it underneath the carpet, but you found the derivative, then you did your job. If I say find the derivative by definition and I see that you used the shortcut, I give 0 points because you did not follow my instructions. Yes? So there are two things: read the instructions, read them carefully, produce the exam just as I request.
Professor, which definition we have to use, the first one and the second, with an H? Doesn't matter, either or?
Doesn't matter either or, and you can ask me questions in case you are in doubt. My goal is not to trap you in that sense. You see, my goal, I hope you would understand it today a little more, is to ensure that you understand how to think in mathematics, how to, well, not just that you solved some silly question from a book, but that you actually are, it's actually improving your thinking. That's my hope. All right, guys, and with that said, please turn the cameras on, please, please, pretty please. It's so boring when I don't see your faces. It's so, you know, Arkady Etkin at Yahoo, yes. So turn on the cameras. I guess you don't want to listen to my pleas. Die Kameras sofort anschalten. Is it better? Yes, when is the, yes, when will they put names? No, I unfortunately do not have any ideas. They do that as when they do that, you see. So the names are not yet there. I personally have no idea what I'm teaching in Brooklyn College next semester. Once I have an idea, that's very soon after the names appear. So it will be close to the end of the semester when that happens, maybe even in the summer. Good? Are we ready? Oh, Grant is here. Yes, then we are ready. Good? All right, guys. So I hope you would enjoy today's lecture, or try to. And because we're finishing, and I hope we will finish today. We are finishing everything we need to know for exam 1. Make sure you are aware that I believe the final is on the 17th of May. I believe, I might be wrong. Just so you have a time frame of what happens. My exams are going to be take-home, right? I'm pretty lenient, I would say, I think. Okay, so if you just show me that you are just doing the bare minimum, I do try to pass you.
Do you have like a time when is the final? Because I have work time, so
if there's a conflict, then you will email Professor Suzuki and he will give you probably a makeup, right? But we will see when it is. It's completely out of my control.
Okay, thank you.
Sure. All right, let's see how many came here. And guys, let's take a class photograph. That's an attendance class photograph. If you want your face to be present, go ahead, turn it on, as I might take that into consideration, in case the consideration is merited. Say cheese. Okay. Oh my, how nice to see more faces. How nice it is to see faces, huh? All right, guys, so today we are going to learn. Yeah, don't worry enough. If you have problems, don't be too afraid unless you have to, right? If you have no reason to fear me, don't fear me.
Professor, I believe I got an email a while ago saying that the final is on the 21st of May on Friday.
Oh, even better. You see, life keeps bringing us surprises. It's later. More time to prepare.
from 1 to 3. But that could be
yes, guys. But I will do everything I can for you if you know the material. You understand? So focus on that factor. Know the material. Understand it, right? I mean, something happens. You were unlucky. Your favorite person left you. Your cat escaped. I don't know, right? I understand, or I try to, right? And I try not to do harm, but know the material. If you know the material, I will do everything I can for you. All right, so today we learn a very important task, right, guys? How to catch a cockroach. Have you ever thought about it? How do you catch a cockroach? Well, a cockroach does not want to be caught, correct? So imagine the cockroach has a pencil attached to its butt. And here is that cockroach, it's running around, not wanting to be caught. What can you do? You can suspend one hand below the cockroach, another right above, and like two police cars chaperoning a suspect, you just narrow the gap until you squeeze. What does it mean mathematically? Do you see that we have this function f of x that I graphed here is a function whose limit is somehow not obvious to us. Good? We don't understand that limit very well. But perhaps if we are very smart and very lucky, we are able to draw a curve, a very simple curve that is, I call it g of x, and another curve on the top, I call it k of x, whose limit I know, and whose limit at the point A is the same value. You see what happens? So as the cockroach runs, we are keeping the same x-axis. It's for the same x, we have g of x is the altitude of the lower hand, and k of x is the altitude of the upper hand. And they are always, so they are always on a vertical line. You see, anywhere the cockroach is located on this curve, they are always on a vertical line. Can you imagine that? And so when do I see the cockroach caught? It's when it's at the point A. I know its limit is that same limit L, which is the common limit of K and of G. So far clear? Let me try to explain how that is supposed to work. So suppose I'm interested in this limit where x goes to 0 of x squared sine of 1 over x. Well, they don't have to be moving to the same tangent line, only that the limit of the easy curves converges to the same value. And the easy curves, the curves that I control, that I understand well, are locking the difficult curve, the cockroach, between them. You understand? So here is that limit, guys. So this limit, I mean, maybe you right away see what the limit is, but it's not so, perhaps not so obvious. Perhaps not so obvious. Do you see why it's not so obvious? Because, well, the limit of sine of 1 over x does not exist. You agree? Sine of 1 over x as x goes to 0, sine will oscillate very wildly. Can you see that, guys? Maybe I'll show you a graph of it. Here we have a graph of it. Give a moment. Here it is. Do you see it? And if I zoom in, you see it becomes completely blue. What happens is as you approach, you see, look at it, we zoom out. So as the cockroach is running, if it's sine of x, as it's running closer, you see this dot, it's running closer, it just starts jumping back and forth from wiggling from top hand to another hand, okay? So this limit, of course, doesn't exist, you see? Sine of 1 over x is just going from minus infinity to plus infinity. But yes, between minus 1 and 1. I said minus infinity and plus infinity, but between minus 1 and 1. That's right. It's nice that I see more people here. Almost everybody registered. Good. So x squared sine of 1 over x. Then look at it, guys. So we can begin designing something. But we begin designing something here, so we can say sine of 1 over x. All I know about it is between 1 and -1. Yes? And so if I multiply this by, look at it, this is just this part. If I multiply everything by x squared, look what I get. Multiply everything by x squared, you get minus x squared less than or equal to x squared sine of 1 over x less than or equal to x squared. You understand? Guys, I engineer that cockroach function, and because I'm so lucky here, I'm right away seeing it's flanked by two very nice neighbors. So this guy, as x goes to 0, will approach 0. This guy, as x goes to 0, will approach 0 as well. What will this guy do then? What do you think? Where can it go? It's flanked on both sides and it's forced to go to 0. Do you all see that? Do you see, guys, what's happening? I flanked it by x squared and minus x squared, functions that I understand very well, limits that I can take very well. So we use the squeeze theorem here. You see what I'm saying, guys? I'm just illustrating the squeeze theorem. Perhaps you could have seen that the limit is 0 with other means. So that answer is the middle guy is going to 0. No, intermediate value theorem is very different from squeeze theorem. Intermediate value theorem, you should recall what it means, guys. Go to continuity, recall what it means. Okay, well, squeeze theorem is what we did. We applied squeeze theorem. Good. So the answer is this. Now, all right, so now let's try another question. Yes, now let's try something like, well, can you tell me, please, what do you think is 1 second. Yes. So here we have something else. We have, let's say, x minus 1 times cosine of 1 over x minus 1 times, well, times, let's say, e to the power of x. Yes. And I want you to tell me, well, let's say that this is to the power of 4, just for simplicity, plus 3. I want you to tell me what's the limit as x goes to 1. Okay, let's try to do this one together. One second. All right, wonderful. Or maybe not wonderful, I don't know. All right, guys, ready? Or you need a little more moments to think about? We will see later in the class the only application where it's kind of useful in the current class. I mean, in other words, this is a very simple example, I hope. Right, so what can we observe? Yes. What can we observe? So observe that if I look at, for instance, cosine of 1 over x minus 1 times e to the x, this is bounded between e to the power 1 and e to the power minus 1, and e to the power 1, sorry, and e to the power 1 with a minus. Do you see that? Because as x goes to 1, this approaches this can approach any value between e to the 1 and e to the minus e to the 1, because cosine of 1 over x minus 1 is between minus 1 and 1. That's the estimate. Clear? And so when I multiply this expression by x minus 1 to the 4th, so we have minus x minus 1 to the power of 4 e to the 1 less than or equal to x minus 1 to the 4th cosine 1 over x minus 1 e to the x, and less than or equal to x minus 1 to the 4th e to the 1. Right, so this part, I can easily notice what happens in this part. In this part, we have that this segment goes to 0. This segment goes to 0, which means this guy goes to 0. Agreed? Which means that in this limit, where just the limit is, as Dolstadt replied, observed, it's just equal to 3. You see that, guys? So we applied squeeze theorem. I just kind of engineered part of it, this part where the answer might have been a little unclear, and I solved it. Here is another one. Ready? So tell me, what is this limit? All right, let's see. Be careful, guys. Okay, I will try not to tell you what I think. All right, interesting. All right, ready? Now let's look at it carefully, guys. So first of all, let's examine the parts. Okay. So let's examine. Easiest possible thing to do is maybe examine x squared e to the sine of 1 over x separately. Yes? So what is that going to do? This is going to jump between what? It's going to be between minus x squared times e. So just let me do it this way. So e to the power of sine 1 over x is between e to the power of 1 and e to the power of minus 1, agreed? So if I multiply that by x squared, I have this situation. And when x is going to 0, this is x squared here, this is approaching 0, this is approaching 0, this is approaching 0, which means that this limit is, of this part, it's 0, only of this part. If I just had this limit by itself, I would see that this approaches 0. Now, can anybody tell me what this is approaching? So this is 0 plus 1, it's approaching 1. So this entire limit is 1 here, right? But what is this approaching? So you're saying that approaches, the other part approaches 0, this is 0. What is this? So what is limit as x goes to 0 root 1 plus x minus 1 over x? What is that? And you don't need to give me just the number. I mean, I would like you to tell me, you see, when you see, guys, you see, if I point to you, I mean, you're not number people really, right? If I point to an animal and it goes, bah, and then you say, when I ask you what it is, you say it is 34A7, right? That's not what I asked. The 34A7 is the ear tag of the goat, but I asked you what is it, and you should tell me it's a goat or a sheep. Do you agree? So don't tell me what is the number. Tell me what is it? Don't tell me the tag. Tell me what is it, please. Well, Moshe, you're telling me the tag. You're telling me 34A729. You're giving me the tag on the sheep's ear. It's serial number, but I'm asking you, what is the sheep? Yes. No, multiply by the conjugate, you are processing it. I'm asking you, what is it? It's you see, maybe you can multiply by the conjugate in this case. I can make it a different thing, and then you would not be able to multiply by the conjugate. It's what Erin said. Yes, that's true. Guys, do you recognize it? This is limit as h goes to 0 root 1 plus h minus 1 over h. And the result is the derivative of the root function, in particular where x equal to 1. Do you see that, guys? You see that this is just the definition of the derivative. It doesn't matter if I use x or any other letters. I'm just applying the definition of the derivative to the root function. So when I say what is it, the sheep is the derivative. The answer, I mean, is just the particular evaluation of the derivative here. Clear? So the result is 1/2 x to the minus 1/2, where x is equal to 1, and the answer is 1/2. You see how I got 1/2? Because I don't have to follow, I can do conjugate there, right? So I can solve this problem by multiplying by conjugate, that's fine, this particular one. But what you want to develop is this recognition, because you can simplify your work tremendously by that. This problem you could solve by conjugates because it's just the square root, but what if I gave you 1,000,000 fruits? So it's 1/2. And so back to the previous problem, what is this? This is 1/2. And so the result of this limit is 1 multiplied by 1/2, which is 1/2. This limit is equal to 1/2. Are you seeing it? Good. And there are a bunch of other examples that I will skip because, well, you get the idea. Yeah, we did those. We can do the ugly ones. It's a bit not interesting. Now, yes. So some students, I'm sure, if you will not admit, you think that I make the class unnecessarily difficult. I always, when I see some people writing some comments, anonymous ones, usually they say this person is terrible and he makes material unnecessarily difficult. Maybe that is true, but the question is, what do you want to do with the material? Okay. Now, questions, the way they appear in nature, let me just try to give you an illustration. Okay, guys, don't worry if you don't understand a lot of what I'm going to say right now, or even anything. except try to understand what sort of level do you need to be at to solve even very basic problems involving calculus, as you call them, real problems, okay? Where it is supposed to be something you use to improve your understanding, okay? So here is a problem that I would like to suggest for you guys. Have you ever tried to stop a moving car by holding a rope to it, right? So if you're very strong, you have like a superhero movie, like, I don't know, what is a Superman? He's like, he's holding a chain and he can hold a motorcycle by the chain or a car by the chain, doesn't matter, right? But most likely you would not like to try this, right? You would not like to hold a chain as a car is accelerating at a high speed, because what would happen to you, you would be receiving road rash. I think that's what you call it, right? You agree? So here is a question, a very simple question, guys. If you take the rope and run it around the tree, like this, right? Around the tree or around some sort of pole, will that help you? You understand? You're not tying it together. It's not tied. You're just kind of holding the rope, but you move the rope or the chain around the trunk. Will that help? Would you prefer to, if you had two choices, either hold the rope around the trunk or hold the rope in a straight line? What would you prefer? Around the trunk, some of you are saying. Now, you are right. At least you're right in some instances. Now, why is that better? So you might say extra friction, and intuitively there will be some friction that would help you, but by how much is it making you stronger, right? So Aaron says there is going to be friction, right? So the friction might help you against the stronger object. Yes, it's true. It can slam you into the tree, but the point is that if you have any hope, in this case, depends, of course, how many times you wrap it around. The question is, how much is it going to amplify your force? You understand? How much, what's the relationship between those forces? So imagine the force B, the force of the motorcycle, is the much stronger force, and the force A is the force you are applying to the trunk. What is the relationship if you are in statics? You understand? In other words, nothing moves. You are not moving and the car is not moving. What is the relationship between the forces? Are they the same forces? If they are the same forces, doing that doesn't help. Is the force B much stronger than force A? In which case, that means that wrapping it around the trunk really significantly improves your ability to stop the vehicle. Do you understand what I'm saying, guys? So by knowing what's the relationship between A and B in equilibrium, I can see how much is my force amplified by friction. Good. And let me show you how you might try to reason that problem, okay? So first of all, you have this type of Lego block reasoning. In other words, instead of thinking about the circle, I will think that it's a polygon with many edges. You understand? So it's a polygon having many edges. So this is the picture, guys. You see? This is the picture, and if I were to draw a part of it, you see, at any point here, so that there is the angle subtended by the rope. Maybe I'll draw another picture here. Here is that tree trunk. And what I imagine doing to the tree trunk, guys, is, first of all, here is the force A, and here, maybe somewhere over here, is my force B. This is roughly the center of the circle. And this is the full angle in which the rope is making contact with the trunk. You understand? And so what's going to happen is that this rope is going to is applying possibly different forces in different regions. So for example, at this point, which is at an angle theta from the first point of contact, the force acting tangentially and in the direction of B, let's call that force tension of theta. Okay, and so what is the, in equilibrium, the force at A is the tension at the zero angle, the tension right over here, and the force at B is the tension at the angle phi. You understand what I'm saying, guys? So if A and B, if tension at zero and tension at phi are the same, then wrapping it around the trunk is not helping you at all. It means that to stop the car, to keep it in equilibrium, your force must be the same as the force of the car. You understand? On the other hand, if tension at zero is significantly smaller than the tension at phi, that means that doing that, you might still, even being weak, you are still able to stop a much stronger opponent. You understand? If T of phi is much stronger, that means that this method of doing it is actually helping. Clear? So then what I can imagine doing, guys, is the following. Look at it. I'm going to try to understand what is that force. And here is what I'm going to do. You see, I can imagine it's made of small line segments. So here it is. I can imagine, let me do it in orange. I can imagine something like, I'm going to exaggerate it just so they can see it. But actually, I'll draw it here very small. You see, so I take this point and look at it. It looks almost like a straight line here, right? And I have this region here, and I have this region here. Okay, so the angle here is some tiny delta phi. This is the same angle, delta phi. So if I zoom in on it, this is what I see. If I zoom in at that region, I see something like that. Good. And so at this point, I'm trying to understand what forces are acting, right? So because I made it, I approximated my circle as if it's made out of a polygon, as if it's made of lots of rough segments. You can imagine that those ropes, the rope is pressing and pushing along the green line. And so what you have is you have the force, the normal force. You can imagine, right, guys? The ropes are pushing against this object. And so here I made the angle sharp so you can kind of see where it is. It's pushing along it, and it's a normal force. And then along this road, I have, like this angle is theta, right? This angle here is theta. So the force acting in this direction is, this is now theta somewhere. So the force acting in this direction is T theta. And the force acting against it, it's here, right over here. Here it is. And it's emanating, I just placed it at this point. It's actually emanating from this point. And this point is theta minus delta phi. So this is T of theta minus delta phi, minus the small angle, you understand? And another force that helps push it in the direction of A is the force of friction, which I will draw in what? In blue. So this is the force of friction that I draw in this direction. That's friction, perpendicular to the normal force. Okay, friction is perpendicular. You understand how the idea of friction, guys? It's mechanically, if you pet the table, you can slide in, but if you press on the table, it's much harder to pet it. So you understand? So the resistance due to friction is proportional to how much you press against the object along which you are sliding. Are you following me? More or less, guys. Don't worry if you don't understand. I'm not teaching you physics. I'm just showing you how mathematics figures out, how you're kind of using calculus, and that's somewhat indispensable, I think. So this is friction. Now, what can you observe, guys? Now, observe the following. Observe that if I project, then first of all, I mean, you can solve it in so many ways, but let's say I look at this angle over here, guys. What is this angle over here? This angle over here is the same as this angle, and the width here is delta theta. So this angle must be, if this angle is alpha, then you can see that this angle must also be alpha, and you see that alpha times 2 plus those angles are the same because this is radius and this is radius, you understand, of the circle. So twice alpha plus delta phi is equal to pi, which means that alpha is equal, this alpha angle over here is equal to pi minus pi over 2, sorry, minus delta phi divided by 2. Are you so far with me? And so the normal force is in balance with this force. You see, this force must balance the normal force. So the normal force must equal to t of theta plus t of theta minus delta phi multiplied by cosine of pi over 2 minus delta theta over 2. You understand why minus? Because we are in statics, guys. If nothing is moving, that means that the net force is 0. That means the net force, we have the normal force, we don't see movement along the radius. We see that the particle doesn't move outwards and doesn't move inwards. Guys, you haven't lost consciousness, correct? Not yet. Yes? Let me just show you the equation and we'll see. Just how many of you are losing consciousness? Yes, right. Lost consciousness, no longer here. Elazar is blacked out, I can see, right? Like in a dive. Okay. Elazar, are you still there? Don't black out. So you see the cosine of pi over 2 minus delta theta over 2. This is just this line, and that line must cancel because the particle doesn't move anywhere. And also in the direction perpendicular to the normal, there is no motion. That means that project t theta to a perpendicular line to this line, you will have a similar result. You will have 0, you see? The normal forces cancels with this red line, and the perpendicular to the normal force must cancel. I hope you understand. If not, it's okay, right? We are just getting to the limit. I'm just trying to show you what part is this thing that we're trying to understand. What part is what I taught you is in solving this problem. So I get those equations, guys, basically, right? I get this equation. Is that, first of all, I notice that cosine of pi over 2 minus delta phi over 2 is sine of delta phi over 2. So I have this equation, and the friction is always a constant times the normal force. On the other hand, I see that if I look at this projection, at the vertical, the difference between T of theta sine of this angle and T of theta minus delta phi sine of the angle must be equal to the friction, minus the friction must be 0. So here is what we get. We get this formula, guys. It's okay. In this stage, it's physics. If you didn't understand and you want to, I will explain more thoroughly after class if you're interested. Okay, guys? And of course, if you're interested, I told you, you can read the physics book. I have one on my website. So what you have, here is where we get it, guys. What you have is this formula. You have that this equation is equal to this equation, to this line, right? Which after rearranging terms, I just divide everything by cosine and then divide everything by tangent of the angle. I got T of theta minus delta phi divided by tangent of delta phi over 2 equals to mu T of theta plus T of theta minus delta theta. I have this equation. It's just, if you understood how I set it up, the equation is an obvious consequence. Here is the equation. Yes? Now, if I am assuming that the tension function is continuous, that means that as I push, look at it, I just converted A to H because the angle is small here. As I push H, it becomes twice T. Look at it, this plus that becomes twice T theta. And now what does this become? Can you tell me? Grant, are you there? Limit as H goes to 0. Can you tell me in terms of T, what is that? Of T theta minus T theta minus H divided by tangent of H over 2. Could you tell me what is this in terms of T? You understand, guys? You understand, Safa? You know, it's not you know, you can multiply by conjugates and those things, but that's not useful in general. In general, you are dealing with abstracts. Like in here, I know nothing about the function T, just that it satisfies this relationship, and I'm trying to understand this relationship. What is this limit in terms of T, please? You are almost there, Moshe. Is it 2T or something small, similar? Look at this. It's what? Come on, guys, recognize it. When I say it's what, I'm not a number. What is happening here, I'm asking. It cannot be a number, right, guys? We don't know what is T. We are just setting up what is known as differential equation. Let me help you guys. Yes, very good. Exactly that. Look what happens, guys. Do you see that? Yes, exactly. Well, Aaron and John. You see what's happening? First of all, look at it. Tangent is not, when H is small, tangent is not, you, Moshe, also got very close, very close. You see what's happening? is that as you push h to 0, tangent is essentially not doing anything. So this is the same as the limit as h goes to 0 of t theta minus t theta minus h divided by h over 2. You see that? I can multiply that by 2 and I get limit as h goes to 0 of 2. And here I have t theta minus t theta minus h divided by h. Does it become something more familiar? You see what's happening? Moshe, your mistake is the derivative. You forgot to say prime, or maybe you meant it. So look at it, you see? I can multiply both top and bottom by minus, and I get limit as h goes to 0 of 2 t theta minus h minus t theta divided by minus h. You see what I'm saying, guys? Now look at it. There is a minus h here and a minus h here. It doesn't matter. It's something that goes to 0. That now is derivative. Are you seeing it, guys? What I have in this form, it's just the definition of the derivative of t. So the result is that this is t prime of theta multiplied by 2. I recognize it's the derivative, and it's 2 times t prime of theta. And this is what we then have, guys. We have this result. We have that 2 times t prime of theta is equal to 2t of theta. Is equal to, sorry, there is also a mu there, right? So it's equal to the coefficient of friction. So it's equal to 2 mu t of theta. No, t represents the capital T. It represents the tension force. That's why I called it T, tension force. You understand? So this is the equation I get, guys, which means I have t prime of theta equal to t of theta times mu. In other words, I'm asking now, basically having this relationship, I now understand that my function is something that satisfies what? That satisfies this equation. I need to find a function, the relationship between the force, the function that represents the force. It's a function whose derivative is equal to mu times the function. It doesn't change the function too much. You understand what I'm saying, guys? So if mu were 1, guys, do you recognize this type of function? If this were the equation, you would have said f of x is equal to what? Derivative of the function is equal to the function. What do you think is f of x? Yes, Grant, e to the x. Right, so that would be, or any scalar, it's any scalar a e to the x. So what the solution to this function is, it means that t of theta equals to, is equal to e to the power of mu theta multiplied by the constant t of 0, which in this case is a. So it's going to be a e mu of theta. So you see, solving this, you get what? What's the conclusion? And I'm not sure if you. So the conclusion, guys, is that the force, by doing that, you increase your force exponentially. Do you understand? What this means is by running the rope around a trunk, you are making yourself exponentially stronger. In equilibrium, your force, the car, in order to be in equilibrium with you, is exerting a force that is exponentially larger than your force, significantly larger. Do you understand? And of course, the amount of contact of the rope with the trunk is, the more contact with the trunk, the more for the more force, the more you have to exponentiate, the stronger is the difference between your force and the force of the car. Now, it's okay if you understood very little of it. My point is this, guys. I hope you see it. My point is that in order to be doing anything interesting with calculus, you have to really, really understand it. You have to know, you see, look at it. The calculus part was what? It's what we are doing in this class was just recognizing that something is the definition of the derivative. You're never going to be asked, so that's why a computer cannot yet do it. You're not asked, find the limit of this function or take the derivative of that. No, that's easy. The hard part is actually figuring out what derivative of what function you have to take. You understand? So you've seen the process, right? We have this process, with this idea that you construct a model of the thing that you're studying. You make a simplified model, which with calculus, you can make in the limit more and more complicated, more and more real. And that gives you that ability to figure those problems. That's why calculus is such a very useful tool. And if you look into the book in physics, or not just physics, guys, anything like this, right? This is what you have to know, and know it very well. It's a very random question like this. It's not a very difficult question if you know the material. You understand? So if you think I'm doing something, if you think I'm teaching something overly hard, maybe we have different goals. My goal is to make you understand the subject. I tried it. Good. Now let's go and talk about trigonometric limits. Remember, guys, so back to squeeze theorem and whatnot. So remember, we have cosine h minus 1 over h. We concluded intuitively that the answer is 0. Remember, we kind of had this intuitive discussion of it. We can actually make it very rigorous now. Here is what we can do, guys. So look at it. We know that this point is 1, 0 on the unit circle. And if I open at an arc h, the point here is cosine h sine h. You see, so we have h is that arc. And now we can measure the length of that blue line. You see, the length of that blue line is root of the difference of the x coordinate squared plus the difference of the y coordinate squared, which happens to be this formula. Clear? So, and you can see that this length is bigger than 0, but less than the absolute value of h. If I square both sides, I get cosine of h minus 1 squared plus sine squared of h is less than h squared, but bigger than 0. When I expand, here I expand it, I can simplify cosine squared with sine squared. They become 1, and plus this extra 1, we get 2. So we have 2 minus 2 cosine h less than or equal h squared. Now I can divide by 2h, everything by 2h. If you divide this part by 2h, you get 1/2 h. If you divide this by 2h, you get 1 minus cosine h over h, and this is just 0. Are you following? I'm not moving too fast, guys. I'm commenting on algebra, but I'm not sure if you process the algebra fast enough. Do you? You understood what I did? I just measured this length, and I concluded that this length is less than the arc, but bigger than 0. And then squaring the length and squaring the length of the arc, I have this equation which I simplify. I have this situation, and then I just divide by 1/2. So I divide by 2h, everything, and I get this equation. And this I can apply squeeze theorem. Look at it. This is a limit I don't know. This limit is 0, and this limit is 0. Remember, we reasoned what this limit might be intuitively, but now we are saying, well, let's do it rigorously. So we don't know this limit again. But using this squeeze theorem, we are able to do it. You see how the squeeze theorem worked? And of course, multiply. So of course, what happens here? If h is negative, the equations, the inequality is reversed, but the result is still 0. And so the limit that I care about, cosine h minus 1 over h, this limit is minus the limit that I was able to squeeze, but that's just -1 multiplied by 0, so I know it's 0 as well. So this limit is 0. Now here is a corollary. Limit as h goes to 0 of cosine h is 1. How do I know that? Now you understand, guys, I'm now thinking very rigorously. Maybe you think it's obvious, because what you do in your brain, you think, well, replace h and plug in 0, and cosine of 0 is equal to 1. But I am now blind to the drawings. I am just using my mathematics to see. So I just found out, look at it. This limit is equal to 0. It means that the function is differentiable at 0, which means that if I zoom in at 0, I will see a straight line segment, right? It means the function is continuous. You understand what I'm saying, guys? Differentiable at 0 means continuous at 0. Yes? So that's why it's a corollary. It's maybe very hard for you to notice, but it's not obvious that this is so. And I even bothered in the proof to show you how I figure out it's 0, because what I do is I engineer out of this limit, I engineer a limit that I understand. So I say, okay, what is this? This is 1 plus cosine h minus 1, which is the same as 1 plus cosine h minus 1 over h times h. You understand why I do that? Because if I know one limit, I can try to write another in terms of it. Here. So that is 1 plus 0, which is 1. We now must develop some more geometry. We need to understand how to calculate circular sectors. So what is the area of that sector? We can think of that, we can generate a formula as follows. So first, look what happens, guys. If I double the angle, the area is doubled. Do you agree? If I half the angle, the area is halved. If I divide the angle by 3, the area of the slice of the sector is trisected. You see that? Which means that the area is proportional to the angle theta. You agree? Proportional means that if you multiply that one quantity, you multiply the other quantity by the same amount. You see? It's like the number of hens is proportional to the number of people, right? If I have 7 people, there are going to be 14 hens. Yes? If I have 14 people, there are going to be double 14 hens. It's always double. Make sense? So the number of people is proportional to the number of hens. Similar here, we have that the area is proportional to the angle. Now, there is one case where we know the area exactly. If theta equals to 2 pi, then the area of 2 pi is pi r squared, because it's the full circle. Okay, so here is what we observe. We observe that we have that area of theta divided by theta is k, is the constant of proportionality, which means that if you take the area of an angle and divide by the angle, it's always the same number, right? If you take the total number of hens and divide by the number of people, you always get the number 2, same number. So k is equal to a of 2 pi over 2 pi, which is pi r squared over 2 pi, which is 1/2 r squared, which means that the area is 1/2 r squared times theta. Did you understand the explanation, or did I go over your heads? You're afraid to admit, because if you say over your heads, I will torture you again, right? It's like I am drowning you in a bucket of water and I ask you, are you getting enough air? Right? Is that what you feel? Or yes, I'm not asking you guys if you want to go into the bucket of water again. Yeah, the tension one is a bit more complicated. I mean, I hope you understand, guys, what I am showing you the horizon, right? I'm saying, where are we walking? If you decide to walk with me on that journey, you're going there to the tension. Yes, it is fun, but it's also very torturous. But you have to be in the right mood for it. I have a great book, guys. I mean, I'm telling you, right? You look at this book and you think, my God, I need to know calculus as good as I possibly can. Better than my left hand. So this is the situation. Good. The area of theta is 1/2 r squared theta. I hope you understood the explanation. It's very simple, guys. If you understand proportionality, it's very simple. Right? Again, proportionality means that if you take the ratio of the proportional quantities, you get a constant. Right? So if you take the ratio of limbs to the ratio, let's say if you have millipedes, right? Millipedes have 1,000 legs. So what would be the proportionality between the number of legs of a millipede and the number of millipedes? Simple question. Write in the comments. A millipede is it's this long snake-like worm that has 1,000 legs. So if I have a bunch of millipedes and I have a bunch of legs, if I don't know how many millipedes I have, and let's not count the legs for a moment. So if I were to take the ratio of the number of legs to the number of millipedes, what number will I get? No matter how many millipedes, no matter how many legs I have. What would be the ratio, please? So you're saying 1 leg for 1 millipede, Sophia? The number of legs divided by number of the number of legs by the number of millipedes is what number always? If they're healthy millipedes, of course. Yes, 1,000. Yes, 1,000 to 1. It depends on how you take the ratio, right? If you have millipedes in the numerator and legs on the denominator, it's 1/1,000. The other way, it's 1,000 to 1. Do you understand? So how do you decide that something is proportional? Let's say you don't know how many legs a millipede has. What you can observe, if you can observe that, is that if you double the number of millipedes, you double the number of legs. If you triple the number of millipedes, you triple the number of legs. If you cut, and don't do that, it's cruel, but if you cut the millipede into 5 parts, you reduce the number of legs by a fraction of 5. You understand? That's proportionality. So we observe that there is proportionality between area of a circular sector and the angle, which means that if I take the ratio of, well, okay, Grant is already, I suppose, engaged in sadism. So we have the ratio of area divided by the angle is a constant k, which I don't know. You understand, guys? The point is that if they are proportional, if I observe proportionality, I don't know that constant. In the case of millipedes, it should be 1,000. Number of legs divided by number of millipedes should be 1,000. But let's say I did not know that, and I just take the ratio and try to find that number. So that number is in general k. Now, at which value am I? And it's k no matter how many. What's the value of theta? It's the same theta. It's going to be k. What I'm doing is then I select theta to be 2 pi, because then I know the area. If it's 2 pi, it's pi r squared. 2 pi means full circle. Pi r squared over 2 pi simplifies to 1/2 r squared. So that k is 1/2 r squared. So you look at it. I just multiply theta on both sides of this equation. You see that I see that area is k times theta, but k is this number. So what I have is 1/2 r squared theta, which is my formula. That's my area formula, area of a sector formula. Make sense? I hope it does. So now we will torture you by understanding why sine of h over h is 1 using this squeeze theorem. Not intuition as we did before, but actually rigorously. So here is what happens, guys. So we have those three shapes. Look at it. Here is, we are taking area here, where h is between 0 and pi over 2. So here we have a triangle with, this segment cosine h, sine h, and 1, 0 cut out. Here we have the circular sector. And it's because it's unit circle, its area is 1/2 h. The area here, it's of any triangle, it's base times height times 1/2. Now height is sine h. You see, height is sine h. Base is 1, so it's 1/2 sine h is this area. This area is 1/2 h because r is equal to 1. And this area, biggest area, this is smallest area, middle area, biggest area. I just draw a tangent here. You remember that? This is tangent. This divided by that is the same as this over that. So tangent of h multiplied by 1/2, the area of this right triangle is the biggest. And so here is what I observe. 1/2 sine of h is less than 1/2 h, less than 1/2 tangent h. Now I can multiply everything by 2 and divide by sine, and I get this equation. 1, you see, I divide by 1/2 sine h. Divide everything by 1/2 sine h, you get 1 less than or equal to h over sine h, less than or equal to tangent h over sine h, which is cosine h. And now I have this quantity, you see, reverse, h divided by sine h. So I take limit, this is 1, and the middle thing has to go to 1. You see the squeeze theorem, guys? It forces the middle guy to go to 1. So if this guy goes to 1, then the reciprocal would be 1 as well. 1 over this, so 1 over this number is going to approach 1 as well. So now we know that the limit of sine h over h is 1. That's very nice. And if the angle is negative, I mean, I just show you what if the angle h is negative, it's h is going to 0 minus. That's the same as minus sine of minus h over h, and I can push the minus down, and I have this, the same as limit as v goes to 0 positive, and that still is 1. You see, I just manipulate the limit for the negative direction very easily. So, good. Any questions? And if the question is, do you have questions about sine and cosine? One of the questions I made for your exam is to see whether or not you can calculate or come up with interesting formulas for sine and cosine. How do you calculate sine of something? How do you calculate cosine of something? Right? In your calculator, you can press sine or cosine of any value and the calculator spits out numbers. How is it doing it? All right, guys. I did tell you what I used to, where I used to work, didn't I? When I was in high school. Exactly. That's why, as I mentioned, if you go to the aquarium, it's a rather poor place. You see no interesting animals. Like most of them are gone. That's during my shift. So here, when you work at the aquarium, you notice all sorts of interesting creatures, guys. So you notice different fish, you notice jellyfish, octopi, etc., etc., etc. So we have different species of functions that we are aware of right now. Yes, we right now know how to take derivatives of x times sine of x, for instance. That's product rule. We know how to do that, and we can take derivatives of quotients. Right? But what's the basic type of function that we are familiar with? Well, here I try to illustrate those functions. So the very, very basic run-of-the-mill fish is your polynomials. You agree? Those are functions that only use multiplication and addition. Now, other functions that you might be aware of are radicals. Yes? Then, of course, you have the EL functions, the inversion function 1 over x. It's called involution. Right? That's a rational function, 1 over x. You can see that it looks like the graph of 1 over x a little bit. Then you have your trigonometric functions, the medusas and its curvy tentacles. And of course, let's not forget the octopus, the transcendental function a to the power of x, the exponential functions. So essentially, out of those functions, you can construct anything else. Okay, you can say rational functions are functions that you can construct out of some combination of the involution fish and the polynomial fish. We know very few functions, guys, terribly few. Those are the species that we are familiar in our very poor flora and fauna. Okay, now suppose I asked you to calculate the derivative of sine of x squared plus 1. Okay, so let's say this is what's happening, right, guys? Sine of x squared plus 1. Imagine a kid is screaming, "Mommy, mommy, sine of x squared plus 1, sine of x squared plus 1. What is the child screaming about? This is a code for what? You understood what I'm asking? So if somebody says that, what is going on? What have you witnessed? Well, jellyfish. Yes, here we go, right? Jellyfish ate the fish, very simply. Do you agree, guys? Jellyfish has eaten the standard fish. That's now chain rule that we're going to learn this way, okay? So it's just recognition that it's one fish that you know has eaten another fish. Guys, why do you disappear? I mean, I wonder. We had a nice photograph, nice class photograph, and now suddenly I see a lot of black squares. You want me to take another photograph? Say cheese, right? Oh, here we go. We now appear. That's nice, huh? I found your triggers, huh? Let's say cheese. Quickly, do you want to say cheese, guys? Those that show faces receive more mercy. Maybe. Okay, good. Oh, you look amazing. Good. All right, so what happens here, guys? Here is the situation. The jellyfish has eaten a fish, a regular fish. We were taught to make a huge fuss about jellyfish not being fish. We would say sea jelly or some nonsense, right? In Russian, it's called medusa. So here is what's happening, guys. Let me be different from my normal way of doing that. I will tell you how to take the derivative, right? So what you do is you cut up the outside fish, fillet the medusa, and that means take the derivative of sine, and you get cosine. You see in its belly x squared plus 1, multiply by the fillet of the inner fish. Do you see that? So it's derivative of outer fish times the derivative of inner fish. You can see, take the derivative, find the smaller fish in its belly, multiply by its derivative. Okay? If you understood it, please calculate the derivative of sine squared plus 1. Can you do that? Moshe, you careful. It's not sine of 2x. Okay. So let's see what's happening now, guys. This is the situation. So we take the derivative. You can take the derivative of 1 separately. The derivative of sine squared. Good. Derivative of sine squared is, look at it. We take the derivative of the outer fish. So it's 2. And I see sine in its belly. And then I multiply by the derivative of sine, which is cosine. You see, so it's 2 sine cosine. Everybody who wrote that is correct. So here we have a lot of exercises. Could you tell me tell me what happened here, and then take the derivative. So for A, what happened, and then take the derivative. Very good, Safa. That's right. Octopus ate a standard fish, or a polynomial fish. All right, so you understand, guys, what's happening? Let's do it together. Exactly, Sarah, very good. So what's happening for A? We see that the derivative of the outer function is e to the x squared times, I see that's in the belly, so times 2x. Clear? If it's clear, please do problem number B. All right. So for tangent, you see, this is x to the power of 1/2. So the derivative of tangent is secant squared, and I find root of x in its belly, multiplied by 1/2 x to the minus 1/2. If you prefer, you can write this as 1/2 1 over root x. Good. Everybody understands? No problem? Good. Perfect. For C, can you solve that one, please? Yes, good, Safa. Good, Aaron. Nice, Sarah. Very good, Alexandra. So you're getting it, I hope, right? So the result is derivative of secant is secant tangent. So it is secant 1 over x times tangent of 1 over x times the derivative of 1 over x. You see, this is first I take derivative of secant is secant tangent, and I just plug what it was inside. And then I multiply by the derivative of what's inside, and that is by minus 1 over x squared, right? You can just think of derivative of 1 over x as x to the minus 1, and the derivative is minus x to the minus 2. Good? Finally, do D. All right. So let's look at what we have here. It says, so you just call it, I call it fillet. right? So we just fillet secant, here it is, and then you just differentiate what's inside, and finally the fillet of e to the cosecant, it's e to the cosecant times minus cosecant cotangent. You see, that's this function, the inner function. And why does the chain rule work, guys? Why does the chain rule work? We will find out on Thursday. It's a cliffhanger, yes? So if you want to stay, ask me questions, or perchance play around of what, when, where, you stay. And if not, then goodbye.